No. Very good. Well, it's a great pleasure to welcome you all to our Zoom seminar, our Zoominar. And this week we have an experimental setup. We're trying to have a mixture of live and I suppose it's called a hybrid seminar, where we have people in the audience, which hopefully you can see if you're online, and we are on Zoom as well. And we tried hard to include everyone. So we hope people in the audience can ask questions, and we've tested that we can hear you on Zoom. And okay, so that's great. Our speaker today is Gian Domenico Palumbo, and he's local to Dias. He's one of our Schrodinger's fellows, and he's going to tell us about non-relativistic supergeometry in the Moore-Reed fractional quantum Hall state. Thanks. I hand it over to you, Gian Domenico.
Okay. Thank you. So, this talk is basically based on a paper that still has to appear on arXiv, and but we are pretty sure that it will appear in a week or so, and done in collaboration with Patricio Salgado Reboledo, that is a collaborator of mine in Brussels University, who recently moved to Poland for his new postdoc. And part of this talk also is based on an already published paper done already with Patricio this year about the Laughlin states, so the geometry of Laughlin states. However, the main discussion here would be really to, so the main topic of this talk is really to have, new ideas and new models to describe the geometry and the topological feature of this so-called Moore-Reed fractional quantum Hall state. Let me start from just the outline to briefly introduce my talk. So I will try to be pedagogical in the first part of my talk. So I'm going to present something that is well known for the people who are already expert in the fractional quantum Hall effect. But I think it's good to remark again some very important feature of the fractional quantum Hall, also for people that are not really into this field. So I'm going to discuss a little bit the main feature of Abelian and non-Abelian fractional quantum Hall states. And then always in this first part of the talk, I will also discuss non-relativistic geometry, how geometry can be seen as an emergent, how we can see emergent geometry appears in the fractional quantum Hall. This was originally an original idea also by Alden and other people who are working intensively in this field. And then in the second part of the talk, I will show to you the main result of our work. Basically, the idea is to describe a specific fractional Hall state, the so-called Moore-Reed state, originally proposed by Gregory Moore and Nicholas Reed in 1991. And this is one of the most well-known fractional quantum Hall states, support non-Abelian anions. It has a very important feature also for application in topological quantum computation. But in any case, I will describe these states from a different perspective. In any case, I will discuss only the quantum field theory feature of this model. So I'm not going to discuss the microscopic wave function, the Moore-Reed wave function. So I will really try to focus on the low energy physics of this state. And in particular, I will discuss also not only the bulk features, but also the boundary feature that usually people consider in terms of the Wetzel-Witten model. But I will present an alternative picture of this boundary theory that has been appeared recently in literature, where an eventual effective supersymmetry could emerge on the boundary of the system. That's why I call this part super CFT and Majorana fermions. And in the last part of the talk, also I will go back to the bulk physics, and in particular, I will try to convince you that if supersymmetry is an important symmetry, at least for the Moore-Reed state, it needs to be broken in any case. And by breaking supersymmetry, we would expect to have a goldstino field. And by integrating out these fermionic degrees of freedom, I will show to you that basically we can go back to a purely bosonic topological quantum field theory that it will allows us to to have the standard to describe the standard topological response of the quantum fluid, like for conductivity or viscosity, and gravitational anomaly associated with the thermal Hall effect. So now let me also, before starting really, let me say that I think it's time to say that we are looking for a standard model for the fractional quantum Hall effect. So for the standard model, I mean an effective quantum field theory that works at the low energy, in the low energy limit in the continuum. So it's a similar, the idea I would say is similar to, the standard model of particle physics, because, first of all, I want to remark some points, I think. So still we don't know what is the fundamental theory for the fractional quantum Hall effect. So there are many fractional states, and it's hard to describe all of them in with a single effective Lagrangian or action. But let me say that this model, I mean, this effective field theory description should be based on phenomenological and numerical evidence, because we have experimented the fractional quantum Hall effect, and there are a lot of numerical calculation, numerical techniques, very advanced, that allows to check many features of this or ideas around the fractional quantum Hall. So it's important that when we think about quantum field theory in condensed matter, we have to be reminded that, it's important, the phenomenology is the core of everything, together with the numerics, because we're talking about many body systems that are very hard to solve analytically in the microscopic regime. And exactly the analogy with particle physics, because in particle physics we have a lot of phenomenology. Thanks to the phenomenology, we had, people have built the standard model of particle physics. Maybe it's not so elegant and simple, but it works. So it's important that the theory has to work. That's a problem. Another thing is that it cannot be derived from high energy quantum field theory. So, I mean, of course, there are many ideas. People work about dimensional reduction of supersymmetric models, holographic models. These are all very interesting ideas and techniques. But I think we don't need really to connect this low energy physics to really fundamental quantum gravity or string theory. So we can borrow some ideas like supersymmetry, like quantum Chern-Simons theory, conformal field theory, but they don't need to be really related to high energy physics. It's something that we have to tailor for, because the fractional quantum Hall exists in the low energy physics, mainly. And important is also that the fractional quantum Hall is not topological only. So it's okay, we associate the fractional quantum Hall to topological order, but it's not only that. So I'm going to convince you that there is much more than topology in the fractional quantum Hall. In particular, there is the so-called GMP mode, that is a propagating mode with spin 2 in the bulk. So it's something that is not cannot be encoded in any Chern-Simons theory. And so a standard model of fractional quantum Hall effect should also encode this geometric and non-topological physics. And even more from the condensed matter point of view, I have to say, as I said before, it's not only topological order, we have also to encode other quantum phase of matter, like a nematic order, ferromagnetic order, superconducting order. These are all appear, they are somehow deeply related in a certain way to the fractional quantum Hall. So it's important to have in mind all these things. And in particular, I have to say that the theory should be predictive, not only descriptive. Otherwise, a posteriori, we can always say that the theory describes what we know, but we should also try to find out a theory that predict new, eventually fractional states or new feature of the fractional quantum Hall effect in general. This was just to put some points in this talk. So I'm going to be speculative, but not too much. This is my, I hope to convince you of this. Indeed, let me start then from just the beginning, very simple, short introduction about Chern-Simons theory in the fractional quantum Hall effect. So the fractional quantum Hall is basically is a gas of electrons at very low temperature that in 2 dimensions on let's say on the plane. So when once you switch on a very strong magnetic field orthogonal to the plane, and then you add an electric potential, let's say in this picture you put an electric field in the x direction, then you see, experimentally, you see a current orthogonal to this potential, and this current is so-called the whole current that is quantized. And indeed, experimentally, we see that by changing basically the filling factor, so the magnetic field also, here we see the quantization of the whole conductivity in terms of h over e squared. And basically you see the so-called plateau. So the plateau is basically associated to this topological number, the Chern number. And basically you can see the integer value. So when you see an integer value here, well, we call it, the integer quantum Hall. And basically, the integer quantum mole is just a free fermion system. So interaction do not play any important role. On the other hand, where there are smaller plateau here, like the rational filling, then this is, this is the signature of the fractional quantum mole. So in this situation, the interaction will become very relevant and important. So we have to bear in mind that these two things are quite different. I think we can say nowadays that we know everything about the integer quantum mole. There are no mysteries about the integer quantum mole, but still a lot of things to understand about the fractional, because interaction give rise always to new phenomena and new physics in the low energy limit. Saying that, so also, as I mentioned in the introduction, I'm not going to talk about a microscopic ansatz wave function. There are many works about microscopic theories, numerical analysis, and so on. So I want to focus only on the quantum field theory description in the low energy limit of the fractional quantum mole. But let me start from the integer. As I said, we know everything about the integer. Indeed, the simplest, the Chern-Simon theory, the Abelian Chern-Simon theory, is a very natural theory for the integer quantum mole effect, because it's a topological quantum field theory in 2 + 1 dimension. And as I say, it's just in this case, it's a U1 theory here. So this completely metric independent theory, this first part. And there is a coefficient here that is an integer number. And again, people call also Chern number. And basically, the simplest way to understand this whole conductivity is to start from effective action and then calculate the corresponding semi-classical equation of motion. No? So in this way, so as I said, this is topological, there is a minimal coupling with the current, electronic current. So when we do the variation of the action with respect to the U1 gauge field, so we get back basically this equation. Let's say I put here only the just a spatial part of the equation, so we have also one for the density, but it's not relevant. So you see this is the equation that comes from the action, and basically tells us that the current is orthogonal always to the electric field. And indeed, this picture here is basically describing the basic phenomenology of this of the quantum mole effect and or conductivity here. I have to say here also in the rest of the talk, I'm going to have I'm going to put E square over H variable 1 for simplicity. But please have in mind that there is always an electric current, electric charge that some people don't like to put, to use the Planck unit. But here, just for simplicity, I will consider this this unit. And as I said again, this nu is really an integer. And more importantly, I have to say that Chern-Simon theory is also able to completely encode the boundary physics of the integer quantum mole effect, because given this 2D electron liquid at a very low temperature, if the system has a boundary, so what people measure is a chiral current that goes in a very specific direction, depends on the direction of the magnetic field that you put. Of course, if you reverse the magnetic field, you change the chirality of the current. And this current is in the integer quantum mole is just a fermion, a Weyl fermion, or basically it's a bosonic mode, it's a chiral boson. And this can be easily described by a conformal field theory, the continuum limit is a Abelian conformal field theory. And this is nice also because this conformal field theory basically comes from the Chern-Simon theory, because we know that Chern-Simon theory is gauge invariant only on a manifold without boundary. When you put a boundary, then there appear, of course, a CFT on the boundary, such that everything, the whole system is anomaly free. And again, this is also well known in story in high energy physics. This idea was even derived before the application in the quantum mole, of course. So this is the integer. It's a very simple idea. Now let's just move to one step further to the simplest fractional Hall states that are called Laughlin states. So these are they were discovered, experimentally discovered first, and then Bob Laughlin proposed the effective ansatz wave function to describe these states. But actually now I'm going to more follow the field theory approach by Wen. Of course, other people, of course, propose an effective field theory. Now, what is the story here? So let me give you just the phenomenology again. So when we have now interaction, no interaction become relevant for the fractional quantum mole, as I said before. And this means that interaction are able to fractionalize the electric charge. And this can be seen just by thinking of this filling factor that now is a rational, is not an integer number anymore. So it goes like 1 over p, when P needs to be positive but odd number for electrons. So I'm going to consider this class of system. Now, if people remember also many work from the 80s, we know that the level of Chern-Simons needs to be an integer. So here we cannot just say, okay, let's put now this 1 over P and end of the story. It doesn't work because the level of Chern-Simons needs to be quantized. So then the trick is simply to introduce an extra degrees of freedom. So an extra, a so-called hydrodynamic field, an emergent gauge field that I call a small a. So again, this is an effective field theory now for the Laughlin states, the simplest one, where again, here we have the Chern-Simon, well, a topological coupling, where here still big A is the external electromagnetic field. And now there is a small a that is an emergent field that comes from interaction. And P now is a level, but it's an integer, you see, so it's well posed this term because the level is quantized. And here, this is not a Chern-Simon, it's a so-called BF theory. So it's a mixed Chern-Simon theory. So everything is fine in this definition. So now the trick is just to say what we can observe are, I mean, the physical observable, the fractional quantum mole, are related to the, let's say, to the topological response of the fluid to external gauge fields. So we can only measure, you know, things associated to external gauge fields, like an electromagnetic field. So we cannot see directly, you know, the effect of the emergent gauge field in our measurements. So the idea is to integrate out in this action, it is complete topological, the small a, and then we get back, again, this looks like, again, the back U1 Chern-Simon theory, but now you see that the level is changed because it's not nu over 4 pi, but it's 1 over p, which is, as I said, the conductivity, the whole conductivity. Because again, you can do exactly the same thing. You calculate the equation of motion, now you get the fractionalization of the electric charge, just because this 1 over p multiplies E squared. Okay, so it's important. Now, another important story, also originally is sorry.
It seems a little strange that I can't just take this theory on its own after integrating out and think a little bit harder what is going on. It must be that the transformations one's thinking of are that we're forcing it to be an integer. There's a little bit more. It looks like it shouldn't have been necessary to introduce that little a field.
No, the little a has another meaning. So this is also associated to composite fermions. I mean, there are many ways how to derive this theory. You know, there are alternative pictures like composite fermions, or, you know, there is a reason why emerge a U1 and new U1 gauge fields. So people have thought also about, you know, this is quite a well assumed idea that, you know, you have an effective field theory. Also, let me say this. So if you have this theory, okay, now you have to look at the boundary. On the boundary is different now. So the boundary, okay, you can still get the, okay, that's what I was going to tell you. So on the boundary now, you can start from this theory, put everything on the open, on a manifold with the open boundary condition. So let's say on the disk, then you will get, let's say on the disk in geometry, you get an edge theory that is so-called the chiral boson theory. Now, actually, the edge theory is not only free fermions. This is the simplest picture, but you can also get the so-called Lattinger liquid on the boundary. And again, this was originally derived by Wen, starting from this effective action. So that's why, again, the fractional quantum mole gives rise to interacting CFT on the boundary as well. And this can be understood completely in this picture, in this TQFT picture in the bulk. So, but as I said, there are other reasons why we believe that the U1, another U1 should appear here. I will tell you again better why. There are another important reason why we expect to have this emergent gauge fields. So later in the talk. So please bear in mind that in the simplest case here, this is still a chiral CFT with central charge 1. So it's jump 1 boson or one fermion, because of course you can fermionize bosonides, depends on your preference. And again, this is completely in agreement with the phenomenology of the Laughlin states that people see in experiments. This is not the end of the story here, because let me now stress another point. The quantum mole effect exists also in the curved space. You can get even more a deeper understanding on the fractional quantum mole when you put on a curved manifold, in particular on a curved surface. Of course, I have in mind curved space only. So time, we don't touch time. So time is completely disconnected. That's why it's non-relativistic geometry. So we have really to think that the quantum fluid is on the curved space surface, and time in that sense does not play any role. And this is important. It needs to be like that. In fact, so there is a new quantity that emerges when you think that the geometry play a role. Background geometry. Bear in mind, I'm talking about just background geometry. So you fix your manifold and it's curved. It's not a dynamical manifold. So there are no fluctuation of the geometry. It's really, you put a quantum mole on a sphere on a non-trivial surface. Now, and then there emerges another idea, another concept, another physical observable that's called the Hall viscosity. So the Hall viscosity in the fractional quantum mole comes from the response of the system to strain or shear. So you can really get a new physics with the curved space. As I said, it's only the space that is curved. This means that there exists a spin connection here that you have to take into account, but it's an abelian spin connection. It's an SO2 spin connection. So it's not an SO2-1. And we know that SO2 is basically isomorphic to U1. And in many people, well, I've done this calculation in curved space and I've generalized the original model that I presented before. And usually the effective field theory depends on the small a, now the capital A, the electromagnetic field, and now the spin connection, the background geometry. And people agree that this theory is the effective field theory for the fractional quantum molecule in the continuum in a curved space. So let me explain to you. Here I already, for simplicity, integrate out again A. So the story, the story works again as before. We integrate out the small a, and then we get all the topological response from external field. So external electromagnetic field and external background geometry. So here we still get the U1 gauge connection, the U1 Chern-Simon theory. Then here now we have the so-called gravitational Chern-Simon theory, but this is abelian again. So you see there is no cubic term for omega because it's really an abelian theory. So it looks like, so omega really behaves like a small a. In fact, there is another important term. So you see also the central charge appears in this gravitational Chern-Simon theory. So this really takes into account the gravitational anomaly associated to the fractional quantum mole when you put on the boundary. Yeah? And then, but the last term is even more important, in my opinion, for the bulk physics. This is called the Wen-Z term. So it was originally proposed by Anton Z and Xiaogang Wen in 1991, more or less. So it's a minimal coupling between electromagnetic field and geometry. You cannot get this in a fully relativistic theory. So if you try to put, direct Dirac fermions in a curved space, you can still get the gravitational anomaly, of course, many other things. But actually, you cannot get this term. It's completely forbidden because this makes sense only when both omega, spin connection, and electromagnetism are abelian. Okay, electromagnetic field is always abelian, but now also omega is abelian. So there is a non-minimal coupling, and this is the core of the so-called Hall viscosity. So indeed, let me just show to you. Even here now, we can get we understand better the phenomenology just by deriving the corresponding equation of motion, right? So by varying the action with respect to the electromagnetic field, we get the density rho, and we get also the current. Now, usually you get in the flat space, of course, you get only this first term here and this first term here, as I showed you before. Because of the geometry, because of this non-minimal coupling, then now there is a correction of the geometry, where now, sorry, I forgot to say, this bar S is what people call orbital spin or shift. It plays a very important role. And importantly, you see there appear the Ricci scalar here, the abelian Ricci scalar. And also there, in the second part, the current, there appear the so-called gravitoelectric correction that comes from the geometry. So it's interesting, when you put now the quantum mole, let's say the fractional quantum mole on the sphere, and you integrate on the density to get the charge, you see what happens, that when you integrate B, you get the flux, magnetic flux. But when you integrate on the surface, this term, you get the Euler number. So basically on the sphere, this term is not zero because the integral of R is just the Euler characteristic of the sphere. So it's a really intrinsic correction to the density of states due to the geometry. And And this also, we can understand again, this action from another point of view by varying now the action with respect to the spin connection, of course. So, and these are of course, these come from the spin tensor. You know, when you do the variation with respect to omega, you get the first term here that comes from, of course, from here. And then the second term, because it's just from the gravitational anomaly. Now, the first term is important because the first term can be also rewritten in this way. So you can write basically this guy here like eta mu, and this vector u mu is basically what we call covariant drift velocity. But the coefficient here is really important, is the whole viscosity. So it's the product of the filling factor, this orbital spin, and the magnetic field. And the value of this depends on the fractional states. So for instance, what I wrote here, so that S bar is P over 2, a P is this 1 over P, if you remember this, the fractional is, you remember nu is 1 over P. So basically, this is only specific for the Lafley states. So for other states, like the Murid that I'm going to discuss later, this acquires a completely different value. So in this, as I said, this is something that people can measure. Actually, there were some experiment some years ago where the people proposed a sort of quantum simulation of a quantum Hall state in photonics. So actually, you can also simulate quantum Hall physics in not necessarily in solid state. You can have a quantum simulator by using photonics, or you can use eventually in future also cold atoms or metamaterials. So people have measured really this whole viscosity in this synthetic setup, and of course they match with the theoretical idea, at least for these states that are very simple to understand. This is just again a part of the story again, because so far I discussed only the topology of the Lafley states. Okay, so whole conductivity, electric conductivity, topological response due to the background geometry. But as I mentioned before, there is another geometry that is emergent geometry that comes from interaction, and you have to take into account also that thing. It's really a fundamental things, and cannot be described by Chern-Simons theory. And let me now give you just a small introduction to this story. So about the idea of incompressibility. So the fractional states are incompressible. So the idea is simple. You can also see from this picture. So if you start from a droplet, it's a quantum fluid. You can squeeze it. You can deform the droplet, but the area. So there is an area preserving diffeomorphism behind, and this is due to also is related to the incompressibility of the quantum fluid. So it's really like it's an incompressible fluid, but it's also quantum fluid. And this tells us several things. So first of all, that interaction gives rise to non-topological effect. This is really energetic effect, because I can tell you in a bit why. Another story is that there is an emergent, as I say, quantum area preserving diffeomorphism in the bulk of the fractional states. And this is also, well, again, let me just give you some very quick details, because it's a very long story. It's also quite a complicated story. People have done a lot of numerics also on this calculation, but let me give you some analytic results. So usually, again, because this part of the story is related to interaction, so we have to take the two-body interacting Hamiltonian. This comes from this Coulomb interacting term. If you Fourier transform everything, so we can write these things in terms of density, projected density operators. So this rho bar are the so-called projected density operators. And it's possible to show. This was shown by Girvin, McDonald, Platzman in the end of the 80s, that this density of states only in the fractional quantum mole satisfy an algebra, a closed algebra. It's an infinite dimensional algebra. It looks like this, you see? And where in particular this coefficient here assume this very specific sign is a sign function here. This is also known even if some people call it W infinity algebra. Other people in mathematical physics, I think they call sign algebra. This was an original work by Cosmas Tsakos in the 80s. So even, again, this algebra was discovered independently from the fractional quantum mole. So you can find also this infinite dimensional algebra in purely mathematical physics context. But at the end of the day, I have to say, this is very really, as Alden said, this is really one of the main points of the fractional quantum mole, and has nothing to do with Chern-Simons theory or conformal field theory. It's an extra piece of the story. And indeed, this piece tells us that there is a mode, there is a propagating gapped mode in the bulk that now, well, we call GMP mode. So basically the GMP mode that you can, is just, is the projected density operator that, act on the vacuum or ground state, sorry, of the interacting part of the Hamiltonian. So this in few words to say that people have studied numerically, also analytically, this mode that comes from this area preserving diffeomorphism. And basically this mode is propagating, is gapped, and carry spin 2. So that's why people start calling him graviton, at least non-relativistic graviton, something that looks like a graviton at leed, in the linearized sense. So I'm not talking about, well, let me be precise. It's not, still we don't have any geometry here. It's very similar to the graviton that you get by linearizing gravity, in the Pauli-Firth theory, no? You have a GR, you linearize on a flat background, then you get the linearized Pauli-Firth theory. That is the analogy. That linearized graviton is the analog of this graviton here. That is not relativistic, it's massive. So it cannot be Lorentz invariant. Any theory here needs to break Lorentz symmetry, even in 2+1 dimension. Now, how to do this is an open question, in my opinion. There are some proposals how to describe the dynamics of this graviton. Maybe I can give you some, I summarize also here. I don't give you more details, but as I said, the original was, the original work is by Gilbert, McDonald, and Platzman, but recently Haldane enforced, stressed this point that there exists an emergent geometry behind the fractional quantum mode. Also, let me stress another thing. So even here, when you squeeze the system, still you can have Landau orbits. So Landau orbits do not need to be really circular orbits. You can completely squeeze the Landau orbit, you still get the quantum mole effect, the fractional quantum mode. So this means that even Galilean invariance is not so important. You can break even Galilean invariance, you still get your fractionalization of electrons, etc., etc. Indeed, you can have a very complicated configuration, and that's why some people think that nematic order plays a very important role here. But I'm not going to discuss this because it's I don't have enough time. Let me just stress what people have done with this graviton. Besides the work by Haldane, so people have thought about alternatives of how to put together things like this work by Gromov and so on. So this is a quite recent work, PRX 2017, where they propose a non-relativistic bimetric theory. Again, it looks like a bimetric theory in gravity, but again, this is not relativistic theory. And it's a theory that takes into account the emergent Abelian gauge field that I mentioned before, the external electromagnetic field, then the curved background. So this G mu nu is the metric of the background, which is fixed, together with an emergent metric that is dynamical, is associated to the graviton, the GMP graviton. So, and what they put all together these things to show that it's possible still to write down a sort of effective field theory, not completely topological, partially topologically, but also partially dynamical, that also, is able to describe in part the GMP spin 2 mode. But there is a problem here. I think it's very nice work, but the GMP algebra is much more than the graviton. Honestly, because of the infinite dimensional algebra, if you try to decompose this algebra in modes, at first order you get the spin 1 A1. So that's why I say that this U1 emergent field U1 is important because it comes from the GMP algebra. It's the first. At second order you get a spin 2, and this is what I call graviton. Then you have to, if you go up, then you would get also spin 3, spin 4, spin 5. So in principle there is an infinite tower of higher spin fermions. Higher spin boson, pardon. Higher spin boson that would appear. This was stressed by another work by Son here, and also by work by Andrea Capelli. I think this is a very important work because it's a very nice way to see how really you take your W infinity algebra, GMP, you decompose, you use basically the Moyal product, you expand in terms of 1 over B, where B is a magnetic field, and then you get an infinite number of modes. And as I said, the first is spin 1, the other is spin 2, and there is spin 3, and so forth. And still, what is the effective field theory for this is not clear. Well, they propose a tensorial new kind of Chern-Simons theory for higher spin, but it's unclear if these higher spin are really just higher spin modes, linearized mode, or they can be embedded eventually. I'm not sure about it in higher spin gravity, higher spin non-relativistic gravity. This is completely unknown field, but I think it's quite exciting research field nowadays. But I will not mention, I will stop here with higher spin. It's still completely, there are very few work and people don't know really what to do with higher spin. I mean, there are numerical work. You have a control numerics, but actually it's very hard to build a real effective field theory with these guys. Breaking Lorentz, breaking many things. Instead, this is much more easy to understand. Now, let me move on because let me go now to the Moore-Reed state that is really the core of my talk. So I wanted to give you really a generic presentation of, what is an integer quantum mole, the fractional quantum mole, the Abelian one, that are very easy to understand, at least impartially. We understand many of the things of the Abelian. The non-Abelian quantum mole states are much more complicated to understand in general. And the simplest one, the most famous one, I have to say, is the so-called Moore-Reed state. As I said, this was proposed by Gregory Moore and Nicholas Reed in this new physics, I think it was a nuclear physics B, sorry, 1991, where here basically there's a new phenomenon that is emerged. So it's called the pairing. So basically, even these fermions can basically, can pair. You can get, so when you have a strong interaction, so it's very similar to the superconductivity. So even polarized electrons can form pairs like bound states, and similar to the Cooper pairs. And basically, they can condense and they can really give rise to a so-called P-wave superconductor. P-waves are beyond the BCS theories that Barden-Cooper-Schiffer. So it's something also very important for application in quantum computation nowadays, because many people talk about the non-Abelian anions, Majorana fermions, and indeed the Moore-Reed is important because it gives rise to Majorana fermions that could be important for to topological quantum computation and quantum simulation. But let me just stress that again, in the bulk physics, this quasi-particle, of course, carrying fractional charge is one-fourth of the electric charge. As I said, there are non-Abelian anions in the bulk. They satisfy the so-called anionic statistics, in particular the Ising one. And in particular, on the boundary, as I said before, there appear not only the chiral boson. The chiral boson is always there, because actually you build the Moore-Reed from the Laughlin in a smart way. So the chiral boson remains, but then there appear another mode, a chiral Majorana mode. And this is really a neutral fermion. So it's not a Weyl fermion, it's really a neutral fermion that appears and carry central charge 1/2. Indeed, the effective field, there is an effective field theory for this already for the Moore-Reed. Many people, many people have worked on the Moore-Reed in many different ways. In particular, there is what people believe is the natural effective field theory is an SU2 at level 2 Chern-Simons theory. And this, why this? Because basically the story, a posteriori looks simple, because if you put now, if you consider boundary, then we know that, the SU2 at level 2 Chern-Simons theory gives rise to a chiral Wetzel-Witten CFT on the boundary. And this is nice because this Wetzel-Witten has exactly the central charge 3/2. So 3/2 you can decompose in 1 plus 1/2. So it's 1 for boson, 1/2 the Majorana. So they are same chirality. So it seems that it match completely all the features, right, of at least of the original proposal by Moore-Reed and the phenomenology of the boundary. The only problem with this story is that here you have to now consider an emergent non-Abelian gauge field. It's very hard to deal with, to couple non-Abelian gauge field with this Abelian geometry. The geometry is the problem now. Can be done partially. I think it's a little bit complicated, I think, to get all the information just from this theory. At least this is my personal point of view. Of course, other people disagree, but that's why I want to give you an alternative picture of the Moore-Reed state. At least I want to keep the phenomenology. I want just to change the effective field theory description for this guy. So how do we do this? So we want to preserve the chiral symmetry. We want to preserve the chiral boson and chiral Majorana, which are very solid points here. So I have no doubt about that. So recently there was an idea instead that an alternative picture that the boundary maybe is described by an emergent supersymmetric CFT. Let me stress why people have, try to use supersymmetry in this case. Let me say this is this is one of the papers that just appeared this year by these people, where they propose a chiral and supersymmetric conformal field theory. Let me just give you some details. So this is the effective field theory that you get on the boundary of the Moore-Reid, with or without supersymmetry. Even if you forget supersymmetry, really this is again the chiral boson, as I said. Some people call Florianini-Jacquier, because Jacquier was, again, in the 80s, the chiral boson was already known in high energy physics. So it's just a rediscovery in fractional quantum mode. But again, so it's anomalous theory, so it does not exist on 1+1 dimension. It can exist only, the chiral boson only on the boundary of a higher dimensional theory, because there is a Toft anomaly, because there is a global anomaly. And as well as the chiral Majorana. Chiral Majorana cannot exist in nature in really 1+1 physics, but only on the boundary in higher dimensional. Just because the anomaly of this guy cancels the anomaly in the bulk, such that everything is anomaly free again. Now, people in this work, and also in the other, I have to say there is I discovered recently there is also another proposal by other people in 2017. They just assumed that, you know, let's relax a little bit the idea. Let's say that what if this chiral boson and chiral Majorana are super partners of each other? Can we just get something interesting if we could just assume that this comes from a supersymmetric CFT and not from an SU2 Wells-Zumino-Witten theory, which is completely bosonic, no? So the Wells-Zumino-Witten is completely bosonic, although contains a Majorana. Is that here we're talking about the supersymmetric CFT. So now this is possible, indeed. This is also, you can see from a different point of view, this theory is really an N1 chiral CFT, a supersymmetric CFT. If and only if the velocity of the boson is equal to the velocity of the fermion. Because here I put there is a reason why I put two different values. Because usually this is not the case. So usually these bosons have the boson and the Majorana have a different velocity. And it's easy to understand why, because the boson is charged. It's a charged particle. The fermion is neutral. So when there are Coulomb interaction renormalize the velocity of the boson. So even if you start from the same velocity, due to the renormalization of the velocity, because of the interaction, the electromagnetic interaction, then you end up always with a different velocity for the boson and for the fermions. So the point is, if it's also there is a supersymmetry, it has to be broken. So that's why also, in any case, they describe this idea that you start from supersymmetric CFT, and then you break it, and then you get an eventually a goldstino on the boundary, right? But this work is done also on the boundary. They don't mention anything about the bulk. But as I say, what happens on the boundary should be a consequence of the physics of the bulk. So I think there is a miss. So if we believe in this alternative picture, then we have to do something in the bulk first, and then everything and the bulk will be a consequence. Even for the goldstino, I mean, if there is a goldstino, it should be first in the bulk, and after it should be another one eventually. I don't know, but this is not clear. But I'm going to talk about more about bulk physics. So this is one. Okay, let me stress. This is one point why supersymmetry could be useful in the Moore-Reid state. There is another reason, and again, I go back to this GMP algebra. So in this, okay, now there is again this is still numerics phenomenology for the Moore-Reid state. So besides the GMP mode that I mentioned to you, this graviton and this area preserving diffeomorphism, many people have done numerical analysis of the GMP, by using numerics. And I think Olalde and other people, and they realize that basically, at least the Moore-Reid will support another mode that is neutral. It's a fermionic. So I just summarized it in the picture. This picture, sorry, is taken by this work by Alden. So here, the magnetorotor, so what you see here, our mode is basically the GMP, okay? Because there is another name, so GMP is also called magnetorotor. The other one is this neutral fermion mode is completely new. I mean, new because in Laughlin you cannot get this mode. So the mode, numerically, you can see just by looking at this picture. Here there is an energy with respect to the momentum, and here there is a bump here. So basically, phenomenologically, this is a sort of, it's a phenomenological plot to see that there is a sort of mode that appear here around the bump. This is an idea again that besides the graviton, what they call graviton, of course, the spin 2, there is now this neutral mode which carries spin 3/2. There is a numerical way to check the angular momentum of this mode, and there are many work, independent work, confirming that this mode should exist and should carry spin 3/2. Now, spin 3/2 is very special spin because, again, it's not spin 1/2. Spin 1/2 or back will be a fermion, not normal Fermi, Dirac or Dirac-like, or a non-relativistic fermion. Spin 3/2 is something more exotic than standard fermions. And for the people a little bit familiar with supergravity, the spin 3/2 is really the Rarita-Schwinger fermion. Is what you get in supergravity, when is the superpartner of the graviton. So in any dimension, even topological supergravity in 2+1 dimension, you have your spin 2 from geometry, and then the fermionic side of the story, the Rarita-Schwinger, that is, is effective field theory for the spin 3/2. That is completely relativistic. Now, again, here, we cannot use any relativistic theory for this because, as I said before, Lorentz needs to be broken first. And this second mode is massive. So we are talking about a neutral fermionic mode that is propagating. So it's not topological, and it's also massive. So we have to find a way to build. Please.
I'm trying to read your graph. What are we looking at here? I mean, you've got KB, KLB. You have an energy against.
The momentum LB is the magnetic field, 1/, the magnetic field, 1/B.
So, and this is the graphs are telling us, because you were focusing on the minimum here, and I wasn't quite here.
The minimum it looks like represent the quasi-particle, let's say, like here also the sort of minimum here.
So we should think of this as a dispersion relation. Is that what you mean?
Yeah, exactly. Yeah.
Okay.
Exactly. Yeah. So that's why I say it's parabolic, it's quadratic, so it's massive in that sense. So it's not linear in that sense. I mean, you see, so it's massive and propagating. Again, there are no, so far there are only there were this numerical work, and just recently there appeared a paper by Emil Martinek with Gromov and Shinserio, this one, where indeed they propose to use superspace to describe this neutral mode. They don't do field theory, of course. Okay, they don't. It's not a field theory paper. It's really about you take your GMP algebra, you supersymmetrize GMP algebra in a smart way, and you get a new algebra, a generalization of the sign algebra that also take into account, now let's say fermionic operators. So in such a way that they embed really, and then they also propose that this mode, so the graviton, is basically the superpartner of this spin 3/2 that people call gravitino. But again, please be reminded that it's completely different from what people do in high energy. So in any case, there could be superpartners. So there are now two numerical or phenomenological ideas. On the boundary, the chiral boson and chiral Majorana are superpartner of each other. And in the bulk, the GMP spin 2 and spin 3/2 neutral mode are superpartner of each other. Now, these two things are so far disconnected. So what I'm going to tell you now is that maybe there is a way to unify the boundary physics and the bulk physics, partially at least. I don't have a full theory for this, but at least I want to convince you that maybe non-relativistic supergeometry can be the answer to at least an effective field theory sense to this story. So let me then summarize the point. So because I want to start from what some, as I said, numerical and phenomenological evidence to build my model. So first of all, we believe now that, we know that magnetic translation replaces usual translation in the fractional quantum mode. Because there is a magnetic field, we have to take into account with the existence of a magnetic field. There is a time reversal symmetry that is broken, so we cannot build any field theory that preserves time reversal symmetry. So these are important symmetry, global symmetry. Then there is another one that for sake of simplicity, I want to keep. It's not important. It's not so relevant, but I need it for simplicity. So I would say that I want to keep the Galilei rotational symmetry. Of course, it works. It's not works also if you break it. But let's say that I want to keep in any case globally this symmetry. In any case, the Laffolin wave function is Galilei invariant. So if you take the standard ansatz in fractional quantum mode, Galilei is there. No problem with that. Then for the Moore-Reed, only for the Moore-Reed. So let's forget Laffolin, let's forget all the others. I say only the Moore-Reed because of the evidence before. Let's keep some kind of supersymmetry. Let's say there is an emergent supersymmetry, and that after that we believe that there is a supersymmetry, we break it. in any case, because at the end of the day, we have to break supersymmetry. And finally, the last point that, of course, all people will trust there is that at ground state, at zero energy, there is an underlying topological quantum field theory for sure. So topology is dominant at ground state. So there are excited states. You are, of course, if you go higher states, there are dynamical modes, or even anyons can become dynamical. But the ground state, zero energy, everything is topological. Okay. So then, how we can build now? Let's build the effective field theory with all these. These are the global ingredients. So the idea, I follow the gauge principle. I gauge them. I gauge all of them. So I start from an algebra. Let me explain to you now the details of the algebra. So the first line is about, let's say, this is basically the Galileo. Okay, on the first line, if this T, okay, of course, P, A, and PB are the momenta, no? Associated to the momenta. J is the, the rotation, right? Because it's only one component, it's SO2, right? So it's only the Abelian one. Then T is the so-called central extension of the algebra. So if you kill, if you kill this guy and you focus only on the first line, you get basically the so-called Parkman algebra. So the Parkman algebra is the algebra behind, non-relativistic systems in 2 dimensions, in 2 + 1 dimension. Now, when you put this, when this central extension is not 0, you get what people call Napi-Witten algebra. So Napi-Witten, again, they proposed this idea for other reason. But actually, this is why it's interesting, this central extension, because this takes into account the non-commutativity of px, py, right? So is exactly what happens in the quantum world, in the magnetic translation. So they do not commute. So you have to, the standard translation do not commute because there is an underlying magnetic field. So I will associate to this central extension the magnetic field. Now, in the last line, there is another extension. This was also proposed in my PhD with my colleague. At the beginning of this year, so we add an extension with another operator that satisfy this condition, and this takes into account the emergent U1, the gauge field, this so-called the small a that I presented at the beginning of my talk, right? Then after we add also supersymmetry, means that you have to play in a smart way. So now I introduce also supersymmetric fermionic operators, and basically this Q alpha are standard Majorana supercharged. And C is the charge conjugation. But now you see it's different here. The anti-commutators or the Majoranas do not give us the translation. Give us basically the central extension. So it's not the standard. Even if you start from, let's say, supergravity and you take the non-relativistic limit, you don't get this algebra, because here is not the correct way to think. This is just peculiar things for this, because there is this central extension that comes from magnetic field. Okay, so that's why I'm not going to talk about any supergravity theory. There is no supergravity there. There's only supergeometry. It's a specific kind of supergeometry tailored on the details of the fractional quantum mode that I want to describe. Okay, please bear in mind this. Okay, again, I'm not claiming that there is any string theory, high energy theory behind this.
Can I ask a question?
Please.
When you look at the algebra, the script T minus Z commutes with everything.
The Z here?
But take the difference of script T and Z, it commutes with everything. So it's in the center of this algebra.
This one, yeah. You are talking about this Z.
Z, yeah. T minus Z. T minus Z. The difference is an element of the algebra, but it commutes with everything. So why don't I just set whatever number I like and forget about it?
No, I think it's a good point. But I need this because to count the degrees of freedom, I need it for a reason. Let me tell you why. Because I need this Z. You see here, Z appears also in when I build my full gauge connection. You see, I have to associate to each generator, a field, right? So this is why I say the J is related to omega. The translation, P, A, P, B are associated to the dry bind. Now the Z, again, is not trivial because I need this extra, it's an extra ingredient put by hand.
Sorry, I'm sorry, I don't understand. If I replace in your script A, this A, the connection, T by T minus Z and T plus Z, T minus Z will have a coefficient omega minus A. and that can be put in, it will commute everything. It won't be a connection. It will be in the center. So it will not do any parallel transport or anything.
This is the center. This is you're talking about the central extension, or is this one?
No, I don't mean that way. I mean the difference of T minus Z is in the, as an element of the Lie algebra, is in the center of the full Lie super algebra.
You are very quick with the algebra there, Val. How can you see that it's in the center?
I take T minus Z and look at their commutators. For example, take T minus Z.
Yeah,
it cancels.
You must have played with this already, because I can't seem to do the algebra in my head.
T with PA is this one. Z with PA is the same on the right hand side. So I take the difference.
You're saying this and this, right? Because you're saying
this equation and the third line and the first line, first entry, and it vanishes. Okay.
J and P have this commutator.
Yeah.
And J, Z
and this one. Okay. Yeah. Okay.
Just commutes with P, for example.
No. My
Sorry, you mean J? You mean J and Z?
Okay, J minus Z.
J minus Z. Yes, I see that one. I couldn't see it with T.
I agree. No, sorry, because
okay, it's J minus Z. It commutes with everything.
Right. No, it's true. J and Z. No, indeed. But
I can throw it as a number.
No, but let me say, yeah, indeed, they look so very similar. Indeed, they appear together, but then they need to be appear together in the theory. So let me show to you why. Yeah.
I don't understand. Sorry. If I take any irreducible representation of this algebra, I can substitute J minus Z as a number. So suppose you want a unitary representation, I call it some number, okay, and then it goes away.
Yes, absolutely. Yeah, that's right. Yeah.
So it cannot appear in the connection.
Well,
it won't do anything to anything.
No, but again, it's let's say it's an extension of the algebra, right? So you just add an extra it's an algebra that you add an extra generator, and then you say, as this, I agree with you that they are very similar. They play in a very similar way. You see, it's exactly, they're basically the same thing. Indeed, also here, you see here also why you see that looks very similar. Also, if you look at this commutator here, I agree with that. I know this, but it's not a problem because, again, as I say, they will have a different meaning, physical meaning also. So it's a split thing. Let me give you the details of this. So they appear indeed in a similar way here. In fact, in the theory, it's also the only difference is here is okay. Here they look very similar. They look okay. It will be trivial. But here, if you you see this guy here, they look different because Z and Z is related to this constant mu2. J and J is related to another number, J0. So if I put equal, okay, it's a completely trivial story. But I'm saying that this algebra is well defined even when these numbers are different and they are not zero. So that's the point. So I would completely agree with you if everything would be equal and this would be equal to this, but it's not the case. Also for Z and J, even here, of course, Z and J here, and well, let's say, yeah, I mean, it's important, this difference, it's crucial, really. So let me show to you why. So because please have in mind, so here there are three independent constants. They have a very physical meaning. I'm going to tell you exactly the physical meaning of each constant, mu1, mu0, and mu0, mu1, and mu2, okay? And they're different from the physical point of view. That's why we need to take into account both of these guys. Otherwise, I agree, it's trivial things. So let me show to you now. So now that we have a connection, so if we believe in this toy model as a very simple idea, we have a connection, as I said. What we can do with this connection? We can build the simplest topological quantum field theory that breaks time reversal symmetry. So which is this theory? Is the Chern-Simons theory. Because I can put this connection now in this, now is non-Abelian in this sense. And of course, this is a trace with all the, the trace takes into account all these conditions here with all this number, okay? So now these things can be decomposed. Of course, first of all, let me write down the curvature tensor for this guy. So decompose in this way, no? So there is the curvature tensor. This is the Abelian for J, the curvature tensor for Z, and for P, this is the torsion-like term. The curvature for T, that is the electromagnetic field, and this is also now there is a part for the supersymmetric part, no? And as you see here also, well, I use here short notation, so I will forget all the wedge product. So this is the Abelian curvature. The F is the curvature of the small a, the spin 1. This is the torsion line. You see also here, that's again, omega and a go together in this sense. So that's why it looks trivial, but again, not so trivial, because they stay together, so one could remove. But let me continue. Also, there is the capital F in this way, gets a correction here, and also important here, the covariant derivative for the spinor, for the spin 3/2, is written this way. Again, you see omega and a, so again, the z and j go together in this sense. But now we have to use the inner product, all the bilinear forms. The bilinear form are important, because now we put all this condition here with the bilinear form inside this guy, and we can write everything in terms of the physical and emergent gauge fields, okay? And this is well, again, it's just a writing of the Chern-Simons in this way. So you see, now there is omega 0, jj, that is associated to omega. So this comes from the gravitational anomaly. Then the mu1 here is the mutual Chern-Simon, looks like the Wen-Z term that I mentioned to you at the beginning. Then you see this zz is mu2, again, is different. So mu2 will give you the whole conductivity part. Inside mu0 would be really related to the gravitational anomaly. So they have a completely different meaning. And so that's why, again, we keep different then. Then there is also a part that comes from the torsion-like. Again, the mix, another term that comes from mixing now the external electromagnetic field and omega and a together. And finally, there is the, let's say, what we call the effective theory for the topological term for the spin 3/2. So this is nothing but the Rarita-Schwinger theory in 2 + 1 dimension, okay? Is topological. So spin, I want to stress this story. Differently from spin 1/2 fermions, in 2 + 1 dimension, spin 3/2 fermions do not propagate, they're topological. That's why it's compatible with the topological supergeometry. That's why the massless spin 3/2 is the superpartner of the massless spin 2 in topological gravity. Now, this is this is what we get from this simple idea to have a single Chern-Simon for everything. So let me stress this. In other words, people start from they put together geometry, Abelian gauge theory in a phenomenological way. Is that here I try to embed both the emergent field and the external gauge field in a single Chern-Simon theory in this way. So now what we can do from this theory? So first of all, we can set the boundary. And because there is a very simple, well, standard Chern-Simons theory, we can just define the so-called the Wetzel-Minowitten term of this. So the Wetzel-Minowitten is defined in this way. And let me stress, this is basically I'm thinking the system is now on the disk, okay? So the boundary is just S1. So I get the field equation for F, the F, total F. And from this I can define the so-called connection that basically what I want to build is the left invariant, the Maurer-Cartan form, okay, this way. So the Maurer-Cartan, this is a standard approach, it's very universal. So once you have the Chern-Simon theory, non-Abelian, you go on the boundary, you get the Wetzel-Minowitten, you define the Maurer-Cartan form that satisfies the Maurer-Cartan equation. And then you have your well-defined Wetzel-Minowitten, whatever is your algebra now, whatever, can be SON, SUN, whatever. Now, for this algebra that I showed you before, we can define all these components of the Maurer-Cartan. We can, once we derive all the components of the Maurer-Cartan, we put back in the Wetzel-Minowitten. And the final theorem, there are many laborious steps, but I will skip them. The final term, so just this can be rewritten in this simple form here. So everything becomes much more physical. As you can see here, there appear indeed a chiral boson in this way as the first part, and the second is a chiral Majorana fermions. So this is just to say that again, this theory looks very compatible with the standard boundary theory of Moore-Reid. One chiral fermions, one chiral Majorana. Of course, now the coefficients are a little bit different, but they're not physical here. Sorry, are physical, but they are associated to this, mu0, mu. Or you see also here. So again, there are the three physical independent coefficients here. So mu2, mu1, and mu0. Sorry, Denjo, how much time I have? I can go faster because maybe I have to start finishing. You know,
we tend not to pressure our speakers,
okay.
as you know. So.
Okay, I am really close by the end.
We like to hear the end.
Okay, yeah, okay, cool. Okay, it's just to stress here, even if there are some algebraic calculation, there are no physics interesting here. It's just that Wetzel-Witten with the right derivation, all the Muller-Cartan form gives you really back the chiral boson and the chiral Majorana. Okay, so this is just that one test that the theory, at least the toy model that I present, looks compatible with the boundary theory. Let's now check what happened in the bulk, because the bulk is the tricky part, and it's something also much more unknown, the bulk than the boundary. Because, as I said, we need to break supersymmetry for a reason again. So the chiral Majorana and chiral fermion cannot have the same velocity. So they have really, we have to break, in any case, supersymmetry in the bulk. Another important point that I say, this theory here is not compatible with the massive propagating spin 3 alpha, because this is a massless, it's topological. So we have to break SUSY also to give a mass to spin 3 alpha in such a way that it becomes propagating. And it looks more compatible with the neutral fermions seen in numerics. So in order to do this, we have to introduce a Goldstino. Okay, now this is a little bit tricky part. Usually, again, people, of course, think about the Volkov-Vakulov theory for the Goldstino. It's actually what people do in high energy physics. I would say that let's keep a little bit more simple. Let's say I can introduce, because the Goldstino is a spin 1/2 neutral fermions in 2 + 1 dimension, okay? So it needs to be spin 1/2. So for this reason, we introduce this effective theory. It's not a Dirac theory. It's topological also because there is a second order derivative. It's topological because it's metric independent. So here there is no, inner product between the gamma matrices and derivative. Still, this theory is not propagating. Looks like, as I said, the Volkov-Vakulov of Goldstino. But if you want to see more details, I advise you to see this paper by Sorokin. So he did all the calculation of the Goldstino in 2 + 1. Actually, the Goldstino, the real Goldstino is not this one, as I say. The Goldstino would have also is non-linear theory. So you would get extra term here. But this is because we are more in the phenomenological low line, we are flying very up, very low. So we just propose something simple that can be useful for our purpose. So if we just consider this spin 1/2, and I call him effective Goldstino, I can show to you that the SUSY is broken because of this guy. So how we can do this? We can just say, okay, I can couple now my Goldstino here with the gravitino in this way by just doing this minimal coupling. So the covariant derivative, as I said, eta is a spin 1/2, is a fermion. So eta is a vector field, is a spinor field. So this is instead is a vector spinor field, the Rita-Schwinger. So you can have this minimal coupling. So if you put this minimal coupling in this story, then you end up with a term that is only proportional to the psi bar psi. And this is exactly what we were looking for, because this is the well-known, at least in literature, Rita-Schwinger mass term. This was originally also said by Desser in the 80s. These things has two things. So this term induced by this minimal coupling gives us two things. Breaks SUSY, because SUSY is not compatible with the massive spin 3 alpha, and it also gives induced dynamics in the spin 3 alpha. That is exactly what we want. So somehow with this Goldstino picture, we have also a mass, and we break SUSY in a way that I think is quite honest. Now, I want to just to give you the last two things, because now what we can do with this massive Goldstino, with massive gravitino, we can just integrate out. Because now, this was shown by Desser also. Desser showed that if you have a massive spin 3 alpha in 2 + 1 dimension, and you can, that really behaves like a massive Dirac fermion. You can count the degrees of freedom, and actually, this is the case. If you have Dirac fermions in 2 + 1 dimension, coupled with some gauge field, you can integrate out if the mass is big, right? And you get the Chern-Simon theory. So this is exactly the same idea. So we have this massive 3 alpha coupled with the background geometry, our background geometry is massive. We integrate out the fermions, the spin 3 alpha, and then we get back this extra contribution, topological contribution. That is Chern-Simons that you see again, omega and A go together as well again. And so this is just to create a sort of a final effective theory that is fully bosonic, because we want to give some, again, as I said, we want to see some topological response in the theory for the physical observables. So another thing that to simplify the calculation, that we require some special condition on the torsion. So actually we kill this part of the curvature, because as I said before, omega, we are in the Palatini formalism, right? So basically omega and drive-by are independent field. So we can vary with respect to omega and respect to drive-by. We will get different stress energy tensor or the spin stress energy tensor. Now we want to fix, so we want to see, a single geometry. So we want to write down, let's say, the drive-by in terms of the connection, spin connection. In this way, we can impose some torsional condition. So in particular, this condition that R is equal to 0 gives it a specific condition on the action. Now, this theory, you put basically back, so this guy here, as you see here, completely replace just this part here, okay? As you can see now, the new theory contains only omega, small a, and capital A, okay? Because this has become a new Chern-Simons. Now, what we do, we integrate out A, as before, as done for the Laughlin states. We want to integrate out the emergent gauge field in order to have only a final theory that only depends on omega and capital A. And it's exactly what happens here. So once you integrate out, you get finally a theory that has a standard Chern-Simons theory, U1, as the integer, as Laughlin, the Wenzi term, similar to the Laughlin that I presented before, and the gravitational Chern-Simons theory that takes into account the gravitational anomaly. Now, the coefficient here, of course, are physical coefficient here. There are, as I said before, the central charge, or well, let's say the shifted central charge, because here you have the nu minus the central charge, that is 3 alpha. Then there is the S, is the shift, and then the nu, which is just the filling factor, the Moore is just 1/2. Now, we can get exactly these physical numbers. So by just choosing now omega 0, omega 1, omega 2, as I say at the beginning of the algebra, no? They are different. They have to be different because omega 0, so JJ, is related to the central charge and the shift. Instead, the other one that appears for ZZ, no, is completely different and only depends on the shift. So they have to be different, this number, because they have completely different meaning. Once we fix a posteriori the value of these three numbers, we have the three physical independent numbers, nu, S, and C. And as I said before, this is exactly the natural response of fractional all states in a curved background. And so far, I can also rewrite, there is also the viscosity, because again, this guy is always related to the all viscosity. We can calculate the equation of motion and we get the all conductivity and so on. So let me finish. So you see, this is again, it's a picture for the Moore-Reid state that now looks much more similar to the Laughlin states, because everything now is back to Abelian physics that is much easier to understand from the geometric point of view. So then I can conclude this story. I want just to finish in this way. So I want also to stress what is missing. First of all, I try to convince you, that maybe non-relativistic supergeometry can play a role in certain kind of fractional states, like this Moore-Reid state, the low energy limit, however. Also, this is we have done two checks to see if this toy model works or not. We have checked if the theory gives rise the right boundary theory of the Moore-Reid, so the chiral mode, the chiral boson, chiral Majorana, and indeed the theory gives us exactly these two modes. And in the bulk, we have seen that there is a massive spin 3 alpha if we break SUSY. And again, breaking SUSY is a good thing in any case. What is missing is the GMP mode. So we don't have a theory for the GMP, for the propagating gravity, because so far I really pushed on the topology. So I think it would be possible maybe to combine this supergeometric theory with the biometric theory by Son and Gromov in a non-trivial way. I don't know. This is a possible idea. And possibly also it would be nice to encode also higher spin modes in this geometric picture. It still is completely unknown field of research, but I think it's very interesting idea. And also finally, I want also to mention that there are many exotic fractional states, non-Abelian quantum states. It's hard to understand all of them in a single picture. So maybe there will be the standard model of fractional quantum world will be really a huge model because I think there is not a single Lagrangian for everything. But at least maybe with this, because we have studied the Moore-Reid, some states like this hierarchy states in the second Landau level, some of them are built from the Moore state. They are called the Bonderson and Slingerland states. Maybe they can also contain some spin 3-half propagating mode, and maybe there is a way to connect them to effective supersymmetry and understand better also them from the geometric point of view, and not only from the whole conductivity point of view. So this is my last point, and so again, thank you for your attention.
Well, thank you very much. That's excellent, and the floor is open to questions. We have real applause today, which is.
Hi, there is.
I have a live question. So in the beginning, when you talked about the fractional.
Sorry, can you, Nietu, can you move a little nearer to the microphone, because we can't hear you online.
Is this better?
Maybe you can come closer to the laptop, huh?
Can you hear me now?
Can you hear her? Loud.
Can you hear me?
Yes.
Who is speaking?
Please.
Is it better?
Nietu is speaking.
Okay.
The beginning, yeah?
Yeah. So when you showed that the form factor in the case of fractional quantum Hall effect, you have to take it to be 1/p, where p is a positive Hall number.
Yeah.
So I just wanted to ask, like, where do you get this condition that this has to be an odd number?
Okay, very good.
Is it an experimental observation?
No. There is no. It's related to the this p appears in the Laughlin wave function.
Okay.
So the Laughlin wave function is compatible only with this when p is an odd number.
Okay.
Or,
and if it is not an odd number, like what goes wrong?
No. Also, experimentally speaking, we see also the odd number.
So this is also an experimental.
Yeah, no. It's also an experimental observation. So there are also they even are more complicated. They even are bosonic.
Okay.
So you can have a p even, but then people talk about bosonic fractional states. So okay, let's say these are built from electrons from fermions, and for how it's built the Laughlin wave function, this p that appears in this Laughlin wave function needs to be odd. That is compatible with experimental fermionic fractional states that people see. So 1/3 is the most famous one, then 1/5, 1/7, and so on. So
Thank you.
Thanks.
But that's a very good question. She's asking, Domenico, because your theory doesn't care. This this theory here only selects any integer. It doesn't mind whether it's even or odd.
No, indeed. No, but that's why there is a missing information. Of course, that's why I said it. So the microscopic theory is richer than effective field theory. So the effective theory is compatible with all the wave function tells you, but the phenomenology is also important. Let me say this. So when you have a p 1/2, for instance, p is 2. Okay, this is also a well-known quantum mode, but it's gapless. So it's a compressible theory. So actually, you lose completely the gap and this GMP. Indeed, it becomes a Fermi liquid basically. This can be misunderstood completely in the picture of composite fermions. And there is an idea, for instance, by Son, this was done in 2015, that if you are looking at this p 1/2, okay, then the effective field theory is the Dirac fermions, it's gapless Dirac fermions. So actually, you see, you can work again. That's why the Chern-Simons need always to be together, other things, other information that in this just single line are missing. But there is this composite fermion picture that people have to take into account. Yes. So. I guess no other question.
Yeah, well, I was interested in your supergeometry, that algebra that I was focusing in on for a second. There's presumably a supergroup associated with this.
It's a very good question. What I can say is the following: it should be a supersymmetric version of the Napi-Witten algebra. So again, the Napi-Witten is well posed, let's say, algebra, as I said, people have studied in many situations. This should be one of the possible supersymmetric extension officially. Yeah, we have to investigate more than all the mathematical details, of course, because as I said, we have built this in order to tailor really, the phenomenology. Yeah, but as I said, for instance, sorry, I have to say, several people are working in non-relativistic gravity nowadays, and some people you find already in literature supersymmetric Napier-Witten, where now instead here we have more in line with the standard supersymmetry, right? Where here there is an operator, there is a P, there is the translation. So this is somehow a supersymmetric extension that takes into account the central extension, let's say the central operator. But it should be a deeper mathematical, group, supergroup here. Yeah, I believe so. In any case, maybe I can stress that when I kill, okay, let me put this, when I kill all the supercharges, I get back only to these three guys here. This is maybe, as I said, we call extended Napier-Witten in our previous work. So if you just consider this one, and this one, they describe the Laughlin states. If you add the supersymmetry on the top, then you move to Murid. This is the Matryoshka. So the Matryoshka is Parkman, Napier-Witten, extended Napier-Witten, and supersymmetric extended Napier-Witten. In the sense of the sequence of operators.
Right. Okay. Do we have other questions? Val, you usually have some additional comments.
Not really.
Not today. Okay.
I really don't understand. I think that, I repeat, J minus Z is in the center of the algebra, okay, as is, okay. So effectively, one can say I am adding some extra U1 charge.
Yeah.
Okay. That's all I am doing, just adding one more.
Exactly. No, it's exactly that. No, exactly that. No, it's just that.
There's no intrinsic meaning to putting this J minus Z in this algebra. It is commuting with everything, okay.
Yeah, no, that's clear, I think, Val. He wants it there for the physics.
It's just for the physics is there, not for the maths. I agree.
But there is no coupling. It cannot couple to a non-Abelian algebra. It is simply some extra U1.
Yeah, it's an extra U1. Exactly.
Yeah. Absolutely.
I don't quite understand how the coupling. There are other questions. For example, in 2 dimensions, the main problem is that rotations are not quantized. Okay, it is in a 2-dimensional case. Okay, so this creates problems on, for example, how does one get Hall effect quantization? It's coming from field levels in some other physics. Okay, that I know. Okay, for the integer Hall effect, the field levels is what is giving the quantization of the Hall conductivity. This new field fraction.
Yeah.
It's not coming intrinsically from an algebraic structure. So I'm wondering how this fact, it is not clear, it has never been clear, why one gets odd denominator rule and so forth, Jain fractionation. I don't understand physically what is.
There is no general theory for the fractional quantum mode. This is a problem. So
no,
I think nobody understands all of them in a single picture. Right? Everything really comes from the phenomenology. I mean, there are many other states which are super exotic, and there are no effective field theory. I mean, there is much more. For instance, okay, there is even more. There are some models that are called Reed-Rezai model. Reed-Rezai is even beyond the Murid. Is a filling factor 12/5. Okay, completely. And then on the boundary, for instance, let me at least give you this. You don't get Majorana anymore. You get so-called parafermions. It's something completely much more exotic, and comes from, of course, there is a deep relation to CFT. But people have just seen an experiment, and they try to build an effective field theory for these things. So actually, it's very hard to predict a new fractional Hall state from the general picture. But that's why I say that we need to build something real that look like a more standard model to predict, is not just to describe what we know already.
Can you point out what is a Moore-Reed state? You said Moore-Reed state. Which one is Moore-Reed state?
The Moore-Reed is exactly, no, the Moore-Reed is this one. The Moore-Reed is what I presented here. So this one is that you have basically, filling factor 1/2, but there is also a pairing. So the problem here is that the interaction give rise to bound states. It's really superconductivity like physics. So the electron condensate in this new quasi-particles, but they are still fractional. So it's a new mechanism that you don't, in the Laughlin does not exist, the pairing, but appears here in the Moore-Reed.
I was looking for a formula. If it is a quantum state, they're either a vector state or a density matrix, but what is the formula? And I don't see a formula here.
The formula for, no, I didn't put, for the formula, no, I didn't put anything.
Is it this Pfaffian?
Yeah, it's the Pfaffian, it's the Pfaffian wave function. So the Moore-Reed is the Pfaffian wave function. So there is a precise ansatz for this.
What is that ansatz? For the Laughlin state, there is a formula. Here, I don't see a formula.
But what do you mean about formula? Formula for
Laughlin state, there is a formula in terms of the coordinates of the electrons. There is a formula, right?
The wave function, you mean?
The wave function. What is the wave function? Yeah.
Perfect. No, also here there is it's called the Pfaffian wave function. I didn't write here, but
the Pfaffian.
Pfaffian, yeah, it's a Pfaffian wave. So you have to use the Pfaffian to build this wave function. But the wave function again, even the Laughlin, is not a solution of the theory. It's an ansatz, so works perfectly, but nobody has proved that it's an exact solution.
So the question will be, why does it give non-trivial braiding relations?
But this is another story. No, okay, but this is because this is another story because this is non-Abelian anions here. So basically, in these states, you can have some vortices in the system. Okay, this theory supports vortices. Now, these vortices support trap some zero modes. Now, so if you have this now system of a bounded state of vortices, zero mode, and you braid them, then you see that they really behave like the so-called Ising anions. So you have to go to this picture of the bulk theory. And again, it's because of this Majorana zero modes trapped in the vortices of the Moore-Reed. They exist because it's superconducting like theory. They cannot exist in the Laughlin or, as I said, the Riedler's eye is beyond this and goes beyond Majorana to parafermions. But again, the phenomenology is huge. The problem is that we have, it's a wild phenomenology. Our tools are quite limited. So that's why many people prefer to do numerics on these things, and that's it.
Can I ask, please? For the non-Abelian statistics, there is a Kitaev story code. Okay, I know. Yeah. I think I have good grasp for the maths that is involved there. Why the braid group is coming in? What is a co-product? There is an algebraic structure, half algebraic structure. Okay, and the Dringfeld double, all these things. Here I don't see anything. Okay. If it were a braiding relation, it should be.
No, but there are. So the Kitaev was inspired by the Moore-Reed. So the core is the Moore-Reed. So everything, all these Kitaev, Majorana, Fermi are part of the Moore-Reed story. This was the original. So there is a way to describe all these things. So the braiding group, the fusion rules. You can use all the braiding fusion category. You can do everything on the Moore-Reed. It is the first one. Before, the Kitaev is just a simplification, I have to say. Kitaev is basically a superconductor. So superconductor means that you don't have the U1 conservation of charge. So you can forget all the charged things and you focus on neutral fermions like Majorana. Here, there are both neutral fermions and charged fermions because U1 is preserved, so the charge is preserved. It's more complicated for that. But you get exactly, the things by Kitaev are different models of a universal class of these Ising anions. And this was the original setup for these Ising anions. So this is the core really of everything. You can do braiding, you can do everything here. I didn't show, of course, for reason of, it's just a 1 hour talk.
Okay. Anyway, just a provocative, very interesting presentation. I have to think about it.
Thank you. Thank you.
I'll go and check the papers.
Okay, thank you.
All right.
Well, thank you very much, Giandomenico. Are there other questions? People in the audience can ask you separately anyway, so we can
Yeah, absolutely.
we can continue the discussion. I'm going to stop the recording.
Thank you.
Okay. So see you next week.
Yeah, take care.
Mm.